And for the sake of the recording, I'll say that you do have my permission.
Thank you. Thank you. All right.
Hello, sir. How are you?
Fine. Thank you,
Hello.
Subhajit. It's all yours.
Yes, sir. Thank you, sir.
Okay.
It's a nice pleasure to be here in your lecture, and we were waiting for this how these caves and casts do in real life. So let's hear from you, sir.
I'm ready whenever you are. Thank you so very much.
All right. Well, let me introduce them. But we are very pleased to have Dr. George Veni from the National Cave and Karst Research Institute in Carlsbad, New Mexico. Dr. Veni is a graduate from the University of Texas at San Antonio, and he said that he chased caves. So he went to Western Kentucky in 1985 to get an MS, or he got the MS in 1985, and then he became a Penn Stater, which of course is something very special for me. He obtained a PhD in 1994 with actually a very dear friend of mine, Bill White. Okay. After that, he worked, he had his own company and he worked there for 20 years, looking at management of caves and karst. And karst is especially important because it is highly relevant to petroleum exploration, highly relevant. Okay. He is now the executive director of the National Cave and Karst Research Institute in Carlsbad, New Mexico, and he is going to tell you all about karst. But for those who want a very simple definition of karst, it is the topography that is formed when rocks that are soluble dissolve. And therefore, caves are part of karst. George, all yours.
Okay, let me share my screen. No, you need to allow me to share.
Yes, yes.
Okay, I'll try it again. There we go. Okay, I assume you can see this.
Very nicely.
Okay, I'll change to presentation mode. All right. So again, thank you very much for this invitation. I'm happy, very happy to speak to the people of India because I've traveled a lot, but I haven't made it to India yet. It's on my list of places to go to. And I've recently had the honor to make some new friends in India. So it's on the goal of getting there sometime. It's certainly a major and important country in the world. But this presentation is an introduction to caves and karst, the worlds below. I will describe and define what karst is and describe caves to some extent. While most people have some idea of what caves are, most people don't understand karst, have not heard of the word, or don't really know what it means. I'll then talk about some of the benefits, some of the challenges that we find in caves, and some of the work going on in terms of studying and exploring them. So, excuse me, I have a bad cough this morning. There's something in my throat, so I might cough on occasion. So, karst around the world. Karst areas, as shown here in blue on this world map, cover almost 20% of the world's land surface. I believe the number is actually larger. I was part of the team that developed this Karst map in 2017, and there was some data that we didn't have. Additionally, there's areas where the karst is not exposed at the surface, or at least, and I'll explain this shortly. The karstic rocks that we're mapping here are not exposed at the surface, but they're buried underneath, but they still have effects on what happens at the land surface. So I think karst actually has a much broader distribution. Of course, if we look at India, India is not a karst-rich country compared to some other countries. The largest, longest caves currently known in India are in Meghalaya, but there is a lot more work, a lot more discovery still to be done there. And some of the people who have joined this meeting are from the Speleological Association of India, a relatively newly formed group that's active in studying the caves of India. And so I greatly look forward to their progress and their activity as times go on. But you see that karst is distributed all over the world. We don't know of karst currently in Antarctica, but that's because 98% of the continent is covered in ice. But it's quite likely that it exists there as well. So, what is karst, though? I mean, I'm using this word, and it's a type of landscape, much like beaches and mountains are a type of landscapes. But this is a landscape formed primarily by dissolving away of the bedrock. And the bedrock is typically limestone, dolomite, marble, and then in dry climates, gypsum and halite, which is rock salt. Common features that we see in karst are caves, sinkholes, in some countries called dolines, underground streams, and the world's largest springs. The photo here is an example from Southeast China. The mountains you see in the background, yes, they were formed by uplift of the rock, but these were not individually uplifted. What we had was a uniform section of rock that was lifted up, and then water dissolved its way downward along fractures to individually separate these things. And between them are large, enormous sinkholes. Eventually the water gathers, it flowed underground through a cave. And what we see with this natural bridge is where a part of the cave roof has remained. Most of this cave has collapsed in, and then the water flows underneath where I'm standing into a cave entrance that's about 150 meters high. So, so this is a good example of a very dramatic karst landscapes and many of the features that we tend to see in karst. Now I'm going to introduce another word. I recognize that that not everyone on the call is a geologist, and I'm a hydrogeologist by training. But this is an important word to understanding karst, and that's aquifer. I'll be using it a lot, so it's important to define it. An aquifer, and actually, let me switch over to there we go, laser pointer mode, much better. An aquifer is an underground reservoir of water, and it must be economically accessible for use. It's an underground reservoir of water. Now, when I say underground reservoir, many people think about underground lakes and rivers, and that is not usually the case. And so here I'm showing you three major types of aquifers. And the scale in each of these is much different. On the left, we have a porous media aquifer. The scale here is microscopic. And so the way a porous media aquifer works is that you've got grains of silt and sand and gravel, and water moves around these things. And sometimes if the material is porous enough, maybe through these silt grains and sand grains, and it goes from where the water enters the ground down to a location where it seeps out through a spring. The water movement, the direction of movement is fairly uniform. The flow rate is fairly uniform. And because the openings are so small, there is a lot of filtration that occurs. And the speed of movement is also quite slow. And so in these sandstone or gravel aquifers, you have them in river valleys, you have them in many other places around the world. So this is a very common type of aquifer. Now, we'll move from the microscopic scale to what might be is probably a life-size scale, a true-to-life scale as you look at this on your computer screen, and that's a fracture aquifer. We have in India great plains of basalt, the Deccan Plateau. You've got granitic rocks. So any place where you have these crystalline, volcanic, or igneous rocks, where the rock itself is impermeable. Water can't flow through the rock, but water can flow through cracks in the rock. You have these fracture type aquifers. Because the openings are a little bit larger, water can move through a little bit faster. And because the water is limited to these fractures, the flow routes are a little bit more complicated. And some of these fractures may be a little bit larger, and so they might transmit contaminants a little bit more easily through this type of system. The third type is the karst aquifer. Now the scale has changed from, with the openings you see here, the scale may vary from microscopic to these holes being large enough to fly an airplane through them. And so the groundwater flow paths are incredibly complicated. For example, water might enter here, some might exit here or go there, some will go up here and go that way or this way or this way. These are the most complicated aquifers in the world. And again, they're formed by solution, by dissolving away the bedrock. And so, of course, I'm going to focus here on karst aquifers. I should also say, I meant to say this earlier, that my institute, the National Cave and Karst Institute, is called Cave and Karst and not just karst because there are many important caves that are not formed by karstic processes. It's just that the largest, generally speaking, the largest, longest, and deepest caves in the world tend to be karstic, but there are many significant caves formed by other processes. For example, lava tubes and basalts, glacier caves, sea caves, and other forms of cave formation. But in this talk, I'm going to focus, because it is an introduction and time is limited, I'm going to focus on karstic caves. So how do karst aquifers form? Essentially, fractures capture water as it rains and transmit that water underground. Now, the water is naturally slightly acidic. It picks up carbon dioxide in the atmosphere to make a weak carbonic acid. And so as the water moves through these fractures, it dissolves them and creates conduits. So let me define a conduit for you. My last definition. A conduit is any hole in the ground that is basically larger than your finger, larger than about 10 millimeters in diameter. Because at 10 millimeters, you have turbulent conditions develop where geochemically, flow dynamics, sediment transport, contaminant transport wise, a hole the size of your finger functions the same way as a cave does. And so think about it. If you've turned on, you go into your sink and you turn on the water is coming out of a pipe that may be the size of your thumb. And sometimes you may have seen some situations, if a pipe has not been used for many years, that rusty or muddy water might come out of that pipe. It's not filtering the water. The water is turbulent and flowing turbulently. So conduits are very important to us because what happens when a conduit forms, it is a more efficient place for water to move. And so water, rather than continue to fight its way through tight fractures downward, will then be drawn into this conduit. And because there's more water in the conduit will then will enlarge at an ever increasing rate. And when that conduit becomes large enough for a person to enter, we call it a cave. And so a cave is just a humanly enterable conduit. Now, how do karst aquifers work? Again, it's the basic hydrologic cycle. Rainfall goes down from the sky, picks up carbon dioxide to create carbonic acid. In the soils on the ground, CO2 is released, carbon dioxide is released from plants into the soil to release more carbon dioxide to make the water a little bit more acidic. Nothing that we really notice. We've all dug into soil in our gardens and no one's gotten burned, but over thousands of years, slowly the rock will dissolve. And so the water will move in follow different pathways into the ground. As a hydrogeologist, we call karst aquifers triple permeability systems, because permeability relates to how easily water can move through the earth, through the ground. And so some water will enter the rock itself, into the microscopic pores within the rocks, and it will slowly move through over thousands and thousands of years. Some water will move through cracks and crevices into the ground. Some may drip into an existing cave to create stalactites and stalagmites. Some of these cracks will enlarge to form sinkholes. These bowl-shaped depressions form to move water quickly down underground. Some water will flow off of non-karstic rocks and then dissolve a pathway downward. But essentially what happens is that you've got these two zones. You've got these dark blue dots that mark the water table. So one zone is above the water table. We call it the vadose zone. And so in the vadose zone, water is moving vertically. It's trying to get to the water table as quickly as possible, as easily as possible. And then below the vadose zone, below the water table, we have the phreatic zone. And in the phreatic zone, all cracks, crevices, conduits, caves, they're all filled with water. And so in this case, now the energy driving the system isn't vertical, but it's horizontal, trying to drain the water off to a valley where the water can emerge from a spring. And we'll have two types of springs, depending on your local geological situation: a gravity spring where the water just pours out into a valley. And then in some cases, the water may go much deeper and go beneath some impermeable rock and then rise as what we call an artesian spring, where the water is trying to reach the water table here, but of course the weight of the water doesn't allow it to shoot tens of meters into the sky. It just pours off onto the ground. And then from here, it evaporates upward. Now, if the water is moving to a valley, and it usually does, sometimes it will go down to sea level or below sea level because sea level has changed at times. But as the valleys go deeper and deeper, what will happen is that this flow path will be abandoned. That's what's happened here, is that at one point the water traveled through here and discharged into the valley in this location. But then the valley became deeper. The water through here was abandoned and went to a lower path. Eventually, as the valleys continue to cut deeper, this path, this flow path will be abandoned, and this will be the gravity flow spring. So karst aquifers change over time. They're dynamic systems, they're complex systems. And in fact, some of these older abandoned flow paths, may be reactivated. During a big flood, water may rise on up and flow out through this passage. And according to the diagram, it goes into the same valley, but it may go into a completely different location, which is certainly important in terms of managing water quality, water quantity, and other factors that are important to us. So in a triple permeability system, people will ask me, how old is the water in karst? Is it thousands of years old, hundreds of years old, hours old? And I say the answer is yes. It's all of the above. It just depends what part of the system you're sampling. So if you're sampling the pore space in the bedrock, the water may be tens of thousands of years old. But if you're standing in a cave stream, that water may only be in the ground for a few hours or a few days or weeks. So these are very, very complex systems in terms of water, their chemistry, contaminant transport, and the like. So one of the difficulties in explaining karst to people is that if I say mountain, you get a picture in your mind. You understand what a mountain is. If I say river, if I say beach, you get a picture in your mind. And yes, there are variations between mountains and different types of beaches and different types of rivers, but the basic picture is still the same. With karst, though, visually, they are different. They look very different from place to place, depending on the local geology, depending on the local climate. So I'm going to show you some different types of karst landscapes from what I call the dramatic to the hidden. And so the dramatic, the visually dramatic karst, some of the best examples in the world are in Southeast Asia. Thailand, Vietnam, China have the best examples, and both of these examples here are from China. And this dramatic karst occurs where the rock is in massive or thick layers, thickly bedded, as we say geologically. And so here we have very few layers of rock. You can see some layers here divided here and here, but generally very thickly bedded. They occur in areas of high to moderate to high rainfall. And they occur in areas of rapid regional uplift. And so China and Southeast Asia has, in essence, they have India to thank for their dramatic karst, because the Indian subcontinent, as it drifted across the Indian Ocean and then slammed into the Asian continent, people think of that and say, yes, it created the Himalayas, of course, but it also uplifted much of Southeast Asia. And so that rapid uplift combined with the thickly bedded rock, combined with the high rainfall, created this very dramatic, world famous karst that we see in China and some other countries in the region. Now, in areas where the rock is thickly bedded, still have moderate to high rainfall, but your uplift is moderate, maybe rapid, we see a less dramatic karst, but still dramatic. Two examples. This up here is from the island of Puerto Rico, and down here is from the Philippines. We'll start with the one in Puerto Rico. If you look carefully, you'll see all of these hills, you know, and between each of these hills are large sinkholes. And the Arecibo radio telescope, one of the largest radio telescopes in the world, about 300 meters in diameter, is nestled inside one of these sinkholes. So if you were to fly over this terrain, it would look like the cartons, that you get eggs in, where you have the depressions where the egg sits, and then you have the higher areas between them that keep the egg separate. Except this goes on for dozens, and if not over 100 kilometers, depending on the location that you're at. And so we're just looking at enormous sinkholes in this area. And so we call this a cockpit karst. The term comes from Jamaica, where these large sinkholes were called cockpits. Now, related to this is what's known as a cone karst, which we see an excellent example on the island of Bohol in the Philippines. In this case, the landscape, the sinkholes have eroded down to form a flat plain, leaving the hills behind. And so we've, in this area, we have what are known as the chocolate hills, because seasonally the vegetation takes a chocolate type of color. But again, these are related types of landscapes formed where uplift is moderate, more moderate than rapid, but again, with moderate to high rainfall and massive to thickly bedded rocks. Now let's move into what is known as the classical karst. The classical karst is, strictly speaking, in what's now modern Slovenia and a little bit of Italy. It's a region known as the Kras region, K-R-A-S. The Germans took the word Kras and made it more German. They call it, and that's where the word karst came from. So they took karst and they made Kras and they made it karst. Now, in the classical, in the classical karst, and in the U.S., the sinkhole plain where Mammoth Cave, the world's longest cave, is located, is our classical karst, but worldwide, the classical karst is in Slovenia. Excuse me. The rock is only medium to thickly bedded, moderate rainfall, not high, and the uplift is low to moderate in the region. And I say here that karst is oftentimes hidden in plain sight, because let's first look down here below in the Mammoth Cave area. If you go through this area, or even here in Slovenia, you'll see a big field, you'll see some hills. You don't see anything that yells and say, "This is karst." It doesn't appear to you. But if you look carefully, you'll see here's a little sinkhole. There's another one. There's another one hidden in the trees back here. If you look carefully in this region and walk through the forest, you'll find many cave entrances and sinkholes up in the hills. But then if you look very carefully at this broad, flat area, this is a giant sinkhole. It's a type of sinkhole that we call a polje, which is a Slovenian word for field, because what happens is this is where they do their agriculture, through much of their agriculture. These sinkholes, these poljes, will flood annually to water the area, and then when the floodwaters recede, they can be planted, and many of the best crops in the region grow in these areas. So again, in a classical karst, many of the features are there, but you have to look for them. They may not be as obvious. Now we have in other areas a subdued karst. This type of karst is, and I'm talking about the topographically subdued karst, and these areas are most common in areas of arid to low rainfall. Uplift can be slow or fast. Bedding thickness can be thick or thin, but typically it's dominated in areas of low rainfall. So this is an example from Texas, where I've spent much of my life working. A very small sinkhole. Most people wouldn't even think of it as a sinkhole, less than a meter in diameter, only a few centimeters deep. But if we move some rocks and dig into this, we might uncover a large and significant cave. This photo is from where I currently live. This is about 30 kilometers from where I'm sitting in Carlsbad Caverns National Park. It's a desert area. You drive past it, you walk through it, you think, oh, there's just mountains. You don't see large sinkholes. You might, if you look carefully, you'll see some small karst features. And on occasion, because this is Carlsbad Caverns National Park, you might find a cave entrance, and this is the entrance of Carlsbad Cavern. What I've been describing here for you has been one type of karst, what we call an epigenetic karst, where water flows down into the rock and then goes down into a valley and comes back to the surface through a spring. But there's another type of karst called a hypogenic karst. And Carlsbad Cavern and many of the caves here in the Guadalupe Mountains are hypogenic. This means that they form by water rising up from great depth and eventually flowing out to the surface. We don't have time to talk about hypogenic karst other than just to mention it. And there are many other varieties and details that we can talk about in karst. But I just wanted to at least introduce the concept to you that there are, again, many different types of karst around the world, which adds to the complexity in trying to identify them and to say, this is what karst looks like. There is no uniform description of what karst looks like, because it's so different depending on where you are. And then there's what I'll loosely call here a hidden karst, and that's our caves that are below the surface. And caves form, as I said, by water moving underground. This is in Lebanon, where this cave has captured the flow of a stream, and it's flowing down here underground. A very large cave. You see a couple of people here for scale. If I recall correctly, the water here falls about 67 meters and reaches down to the water table. And then here's a cave in Italy where you have an underground stream flowing through this cave. So karst aquifers are the only type of aquifer where you really do have underground rivers and lakes and streams. But in other types of aquifers, you don't have them, but you do have them in karst. So let's talk a little bit more now about caves, karst, and water. We'll start talking about why we care, why we should care about caves and karst. And so karst aquifers, as I've mentioned already, they're the most complex groundwater systems in the world. So here's just a hypothetical diagram. Let's say water seeps into the ground in this location. It will go vertically down toward the water table, which is marked by this blue line. But then it'll hit some horizontal bedding or fracture and move horizontally, drop again, move horizontally, go horizontally this way. Some of it will drop down to the aquifer. Some of it can be pumped back up for use through a well. Some may trickle in slowly and contribute to this underground stream. During high flows in the aquifer, some of the water may rise up and go into a different flow path that may join this cave stream, or it may go to someplace completely different. So very complex systems. And as this diagram shows, we have potential sources of contamination because people will use sinkholes as trash dumps. There's many other sources of contamination. For example, where I start the water flow here, the septic field, where their human waste is going out into the field, and how that can move on down quickly into the aquifer. And so as a result, karst aquifers are the easiest aquifers to pollute. I took this photo when I was a graduate student in Kentucky, my friend here is standing in the aquifer. He's standing in the water. We've got water flowing from this upper passage down this wall into the lower passage. So we are walking and standing through the aquifer. Now, the black material you see here, we've scraped it clean in this spot, but the black material you see, we tested it, and it was sewage, oils, grease. It had 14 cancer-causing chemicals in excess of drinking water standards. This cave was not safe. Certainly the water was not safe to drink, and it was not being used, for drinking because of these problems. Additionally, we had fumes in the air. And so this meter would tell us if it was safe for us to continue to explore and study this cave, or if we had to go out and get the spacesuits to continue. And I'm being serious. This is just a very polluted cave. The fact that we are walking through the aquifer, and at this point the water's shallow, but there's other places where you have to swim and even go diving to explore the cave. But the fact that we are walking through here and we are not being filtered out tells you how easy it is for things that are much smaller than us to get into the aquifer. Oils and grease, chemicals, they're much smaller than us. And so if we're not being filtered out, these bacteria and chemicals are also not being filtered out. Karst aquifers are also the easiest to deplete, to make them go dry. Here's an example of an underground stream. It's discharging as a spring in the Czech Republic from Pumpva Cave. So let's say that you were looking for water, and you went back here into the hills and you drilled and you happened to intersect this cave stream. What happens many times in karst is people find cave streams, or usually they'll find smaller conduits, but these conduits produce a lot of water. This cave stream can produce a lot of water at a point in time. But over time, you can deplete that water. You can pump more water that's being produced. It's much like going to the bank. How much money you have in the bank really depends on how much money you make and how much money you take out. If you take out more money than the money you put in, than the money you make, you'll run out of money. And the same thing happens with karst aquifers. People will drill into it. They think, oh, I have this huge water supply, but then they pump it at an unsustainable rate. And so there have been places around the world where karst aquifers have gone dry because people are just pumping them too quickly. They are misread. They misread, they misunderstand the ease of getting the water with the amount of water that's available. But karst aquifers are the primary water supply for about 700 million people around the world. So they are very important water supplies. And so when I talk about these problems, how easy they are to pollute, how easy they are to deplete, I say that not to say, not to say we can't do anything with karst, but I say that so that we can be aware of the issues. I'll often say that when I get into my car, I put on my seatbelt because I realize that I can die driving my car. And so I put on that seatbelt to protect myself. So when we work in karst areas, it's good to put on that seatbelt, to be aware, that problems can happen. So we put on that proverbial seatbelt to try to protect ourselves and try to avoid problems. Some of the problems that we have are land use challenges, sinkhole collapse. These are collapsing down into some underlying cave. This one here is about 100 meters in diameter. You can see it swallowed a number of buildings, some homes. The one here on the right occurred in the middle of a road. The black material you see here is asphalt. It's from the road. When this occurred, this one occurred very suddenly. The one on the left occurred over a period of a couple of days, but this happened instantly, and 5 or 6 cars were trapped, in the collapse. Fortunately, no one was hurt. And when it collapsed, of course, sewer lines, water lines, other infrastructure were damaged in this collapse. In the United States, we see an average of $300 million per year of road damage from sinkholes. Only road damage. That's the only thing we've been able to reliably measure. That doesn't count the damage caused to the vehicles that were here that were destroyed or damaged. This doesn't include places away from the roads where entire buildings have been swallowed and all those properties, where lives have been lost. If we looked at all of these damages together in the United States, we're looking at easily, in my opinion, over $1 billion US dollars worth of damage each year. But we don't think about it. It rarely makes the news because these collapses are scattered over space and over time. So one might happen in one part of the country and cost $50,000, somewhere else $10,000. A few months later, something happens someplace else, $20,000. Maybe once or twice a year, you'll hear of something really big that costs $100,000 to fix or more, or maybe it was in a bad location for whatever reason. It made the news, but generally you don't hear of them. If all the damage happened at once in one location, like a flood or a fire or an earthquake, we would notice it. It would be in the news. But the tremendous amount of damage that occurs, we don't hear about it. And I'm presenting numbers from the U.S. because this is where I have data. But we have sinkhole damage occur around the world wherever you have caves and karst. So let's switch from the geosciences and talk about cave life. When you have space, that space will be occupied by various things. Water is one of the things we've been talking about, but life is another thing. Now, there are various types of cave animals in different groups. We'll start here with my cat, Cueva. Cueva is Spanish for cave because I found her in a cave. Cueva was nearly dead of starvation. This was 16 years ago when I found her, and she's still alive and well, even though she's quite old now. But she is classified, and we are classified as accidentals. We accidentally go into the cave. We'll go into a cave for some temporary need. In her case, she went in there for shelter and got lost and nearly starved because there's no food for a cat or for a human. She's not adapted to living in caves. Humans are not adapted to living in caves. And so the classification of cave animals is based on adaptation to cave light. So the lowest form of adaptation is what we call a troglazine. The troglazine. These are animals that have some level of adaptation to live in a cave, but they must return to the surface regularly for some reason. And typically it's to feed. My friend Shirish, who's on the call here from India, he studies birds in caves. They are troglazines. Bats are the most famous troglazine. They shelter in the cave during the day and fly out to feed at night. Less known, but very important to many, many cave ecosystems, is the humble cave cricket, which again shelters in the cave during the day and comes out at night to feed. And so they start to develop various adaptations to live in caves. As those adaptations develop a little bit further, we have troglophiles, friends of caves, based on the Greek. This salamander, for example, a troglophile is an animal that can spend its entire life underground, but it doesn't have to. And so in the case of this salamander, it has a slick, moist body. It has some elongated legs, appendages to navigate a cave better in darkness. The moisture is because the cave environment is moist. These things will live their entire lives underground in caves, but sometimes you might see them on the surface as well. The most cave-adapted animals are what we call troglobites if they live in air-filled parts of caves, or stigobites if they live underwater. These are the most highly cave adapted. And so what the adaptations do over time, what evolution does over time, is it recognizes that a cave environment is a food poor environment. It's an energy poor environment in terms of food, in terms of nutrition. Our major source of food energy is the sun. Photosynthesis causes the plants to grow. Herbivores eat the plants. Carnivores and omnivores eat the herbivores. And basically bacteria get to us all, microbes get to us all in the end. But what's missing from a cave environment is the sun. So the food sources you have are basically decomposing organic material that do not have a high energy content. And so some of the adaptations you see, both of these are white. Both of these troglobites and stigobites are white. Pigment is to protect you from the sun. It takes energy to produce pigment. So why spend energy producing something you don't need? And so evolution has got rid of the pigment. If you look closely, you'll see there are no eyes. No eyes. You don't need eyes in total darkness. It takes energy to maintain eyes. Evolution gets rid of them. Compared to their surface cousins, we also see some other differences. For example, with this millipede, its legs are about 3, maybe 4 times longer than its cousins on the surface. The same thing for its antenna, much longer than its typical cousins on the surface. Here with these amphipods, its antenna are much longer than on the surface. And the reason for that is that it helps to navigate underground in darkness. It's much more energy efficient. There's other adaptations. They have fewer young because the environment won't support a large population. They also tend to live much longer than their surface cousins. So these are all adaptations to living underground that these cave animals have. And so we have many unusual, unique species living in caves. And I expect that hundreds of new species will be found in the caves of India. It's just a matter of going out and doing the research, because these are isolated environments. You know, unlike a bird which can fly, let's say, from Asia to Europe, or even perhaps to the Americas, you know, which it would be quite unusual. But that bird can go out and breed over a broad area. But in a cave, you know, it can't do that. It can't breed. It's limited to the cave, and so it's isolated, and it evolves in each cave or in each karst area to form a unique group of species. So what are some of the benefits we see from cave ecosystems? And this is where I'll focus on bats. The photo here is from Bracken Cave in Texas. Bracken has the world's largest bat population, usually between 16 to 20 million bats living in the cave. And so what we see from bats alone, we have over 450 foods, industrial products, and medicines that are directly or indirectly resulting from the different activities that bats do. Over 450 different foods, medicines, industrial products. So people often look at these things and say, oh, they're pests. Well, they don't understand the benefits that they provide to us. For example, what they really do is the bats aren't pests, but they provide pest control. Now, this is a Doppler radar image, a weather radar image of Bracken Cave. The blue-gray area is mostly ground clutter from the radar. You can ignore that. But look at these other light blue-green areas here. What you're looking at here, and this is from here to there, that's about 60 kilometers. That is the Bracken Cave bat flight, where they're flying into the sky in the evening. These are flights from other large bat caves in the area. And so they fly out at night and they eat a number of agricultural and other pests. In the United States, bats save American agriculture an average of $23 billion each year from pesticides, from chemicals that they do not need to put on their crops. If it wasn't for bats, farmers would spend about $23 billion a year more to protect their crops from these pests. And that $23 billion doesn't include the cost, the benefit of not having those chemicals in our food, in our streams, in our environment. That's just in saving those chemicals alone. So they are incredibly important in many, many ways. Now, another benefit from cave ecosystems are microbes. Certainly some microbes are being studied carefully for medicinal purposes that can protect us and help us in many ways. But microbes are also, we're finding, are cave creators. Because while, yes, caves are formed by water dissolving away the rock, much of that process is helped tremendously by microbial actions, such as these microbes here that we call beads on the string. So microbes are incredibly important in a variety of these processes, and we're just starting to study them. Now let's switch away from biology to culture. Prehistoric cave life, human life, people living in caves. There's this myth about people living in, far and away into caves, and you'll see cartoons and drawings with stalactites and stalagmites and people living far into the darkness. There are examples where some people have lived in the past in such caves, but they're pretty rare. The reason is you wouldn't want to live in a house where your roof was leaking and had stalactites, dripping water down on you, pools or streams forming on the floor. It just wouldn't be comfortable. Additionally, if you live in a true cave that goes back into a deep, far dark zone, there's going to be air currents through that cave, and so it'll be drafty. If you build a fire, you won't be able to heat up your area very well because the heat's going to be lost both further into the cave and then out through the entrance. The reality is that prehistoric people who lived in caves didn't live in caves like this, but they lived mostly in shelter caves, which have a relatively large entrance, but they only go back a few meters, maybe 10, 20 meters at the most. They're dry, they're out of the wind, and because they have a back wall, if you build a fire, and then especially if you build a screen made out of animal hides in front of you, you can create a nice warm place to live and to survive. And so the idea of people, cavemen, cave women living deep in caves, no. There were some people who lived in cave entrances like this, but mostly they lived in shelter caves, a different type of cave. So if they didn't live in caves, what did they do in caves? There's evidence that, that ancient people, prehistoric people, went long distances underground. On the left, we see cave paintings, 35,000-year-old cave paintings from Grotte Chauvet in France. And I should say this is Grotte Chauvet 2. This is an amazingly accurate replica of the real thing. The real cave is closed to protect it. But this is amazingly, as someone who's an expert in caves, when I went through this cave visually, I couldn't tell the difference between this and the real thing. But these fabulous drawings, that were done in these caves, we believe that there some ritual may have been involved, maybe recording of some important events in history of some hunts, that occurred back then. We don't know for sure. But other places, much more recent history, about 1,000 years ago, these incense burners were deposited in a cave by the ancient Maya in the Yucatan Peninsula of Mexico. And so with the Maya, we do know that they used the caves very much ritually, because they didn't just leave cultural artifacts behind, such as these incense burners and other objects, but they would also draw in the caves, like you see here in Chauvet, but they would write on the cave walls. If you can see the photo of me somewhere on your screen, behind me is a hieroglyphic text from a cave in Guatemala called Nachtunich. And so this is describing rituals and activity that the royalty would come into the cave to perform. And in this cave, Nachtunich, there's also drawings of some of these activities, very realistic drawings. So, so caves were used for ritual and art as sacred places around the world. And so let's talk a little bit more about this. From prehistoric to modern times, caves have been used both as natural resources and as sacred sites in the geography. So let's look at natural resources first. Once gunpowder was discovered, people began to realize that cave sediments, not all, but some cave sediments are rich in nitrates, which you need for gunpowder. And so this is an example from a cave in the US in West Virginia, Oregon Cave, where they have these vats from our Civil War, which happened, 160 years ago. And they would go in there, dig up the sediments in the cave floor, and then leach out the nitrates, and use it for gunpowder. Another example of resources, a rather unusual but example, is from Japan. Narusawa Icicle Lava Cave has deep deposits of ice, and they would be cut out and then brought to the emperor or other ruling class people for their use, for their enjoyment, for their cold drinks on a hot summer day. Other caves have minerals that would be used for medicine, for ritual, for practical purposes like pigment and so forth. So caves have been mined, for many, many purposes over thousands and thousands of years. But of course, caves have also been used for water. And for this, I'll go back to the Maya area. Mesoamerica, as it's known by cultural anthropologists, is the area of southern Mexico, Belize, all of Belize, all of Guatemala, a little bit of Honduras, a little bit of El Salvador, where the ancient Maya used to live. 70% of this area is karst. And most of the water is not on the surface. It goes underground. And so people would go into caves for water. People would also observe in this area that warm, humid, outside tropical air would enter caves and cool in the cave atmosphere and form clouds. And so the ancient Maya believed that caves gave birth to the clouds in the sky, which caused it to rain on the fields, which allowed the whole cycle of life to continue. And of course, they would go into caves many times for water. They would see sinkholes that were certain sinkholes called cenotes that collapsed down to the water table where they would get their water. And these are large chambers here. I should point out that there's some people here. There's one of our tents. So very large chambers. And so as a result, in Maya society and to other societies as well, but in Maya society especially, caves were critically important in mapping the sacred geography of the region. And so what do I mean by that? Is that we know temples that have been built over caves. We've learned through experience and research that in many cases, it wasn't the temple by itself that was sacred. It's the cave underneath that made it sacred. We also learned that they would build many of their communities around caves and cenotes and so forth for the practical aspect to water, but also because of the religious aspect. Their most powerful gods would live in caves. And I know the Maya area better, which is better than most areas, which is why I'm carrying on more about that. But we see similarities in this behavior around the world where caves are considered sacred. In India, I believe the Ashanti caves, if I'm pronouncing the name correctly, are sacred cave painting sites, that you have there. Now, climate change is a big issue. It's a big problem, growing problem around the world. And one of the things that's happening is that we're recognizing, climate scientists are recognizing that caves are the richest source of paleoclimatic and paleoenvironmental records. For many years, hundreds of years, people would recognize that they could find old bones in caves. Remember that diagram I showed you, showing you how a karst aquifer works, and you have these upper level passages where water no longer flows. Well, once water no longer flows through that passage, it becomes a time capsule. And so whatever is deposited there stays there. And so here we see these Ice Age bones left in this cave from over 10,000 years ago that are just sitting there preserved as if they were just deposited a few years ago. And so bones and other materials are preserved beautifully in caves for all sorts of research of past climates and past environments. In the 1970s, a new technique became popular, became known, which is to study speleothems. These are examples of very tall stalagmites from a cave in France, Aven Armand. And it was discovered that within the crystal structure of these amazing speleothems, as we call them, these stalagmites, if you study the isotopes of oxygen, carbon, other elements, it will tell you about temperature and other climatic factors that existed in the past. And then if you combine that by studying uranium thorium isotopes that are also trapped in those crystals, it will give you the age of these crystals. So you can use this to go back and study past climates and put dates on them, much like you can carbon 14 these bones and put dates on this. Additionally, we have a unique variety of sources of information in caves, and I'll show you two examples here. One of which is ice. This is from a cave in Austria, where you've got this thick ice deposit. You've got layer upon layer upon layer of basically climatic history preserved here in the ice. And unfortunately, because of climate change, much of this ice is melting rapidly. So it needs studies as soon as possible. And so in this ice, again, you have oxygen isotopes. You also have pollen, spores from different plants, bones, a lot of material trapped in here to help reconstruct the climate. In fact, if you think of the island of Hawaii out in the middle of the Pacific Ocean, you think of it as a beautiful tropical island, but at the top of its highest mountain, there are caves up there that have ice. And so this tells us these ice deposits are the only detailed climatic record that we have of climate in the middle of the Pacific. And they're being studied now. And one more photo, taking you back and inside of Bracken Cave. My friend here, she is standing on guano, on bat guano, the droppings from the bats. We were doing a geophysical study, these cables and the electrodes here in the ground, to determine how deep the guano is. And it's about 30 meters deep where she's standing. This guano, the reason we're doing this study is to go into the cave, and we haven't gotten to this part of the research yet, and to drill down and to remove a core of the guano, which will have insect parts, pollen, spores, bones, all sorts of other material, in a part of the world where we don't have ice caves, we don't have peat bogs, that you find on land for paleoclimatic work, but it will give us a tremendously rich record of the paleo environment of that region. And so there is great work being done to study past climates by going to the poles and studying ice cores, by going into the oceans and studying deep sea sediment cores. But that tells you specifically what happened at the poles and in the middle of the ocean. Whereas our interest is, what was it like where we live? We don't live at the poles and in the ocean. What was it like where we live? We've got hundreds of thousands of caves around the planet that if we go in and study these things carefully and responsibly, we can build detailed climate models to know exactly what the situations were like, what the climate, what the environment was like in the past in our location, and then use that to build better models to project what climate will be like as climate continues to change. So economic resources, the most, well, let me first say, there's a type of karst known as paleokarst. This is a karst landscape that formed long ago, and in geologic processes shoved it deep into the subsurface. And within those large conduits and caves and pore spaces, economic materials developed and formed in them. The most commonly used one, the most economically important, is oil, petroleum. The pink areas that you see here on the map are major petroleum areas in the world, and most of these are at least from carbonate areas, from paleokarst areas. And you see that most of the most famous major oil producing regions, like the Persian Gulf, Libya, the North Sea, Venezuela, parts of the US, many of these areas are paleokarst. And so we benefit from another type of karst in this situation. But not just oil, but there are other important minerals that form. Bauxite, which produces aluminum, lead, zinc, copper, phosphates, plus plus 24 more economically important minerals occur in these paleokarsts. These are, again, often buried deeply, or at least they were at one point, and some of them have now been eroded and appear at the surface. But so we get many benefits from karst that we're not aware of. But the most important benefit, when people talk about economics and talk about karst, they often completely forget about the most important economic resource, which is water. We talked about this earlier, but we can live without oil, we can live without these minerals, we can't live without water. It just comes down to that simple a fact. And so it's important that we recognize the economic value of water in karst areas. So I'm going to move away now from the sciences and the resources and the benefits and challenges and talk about something more fundamental, which is caves, karst, and the human spirit. Why do we explore caves? Why do we even go into these things? And that is because as humans, we're curious. Yes, we have some needs, but our curiosity forces us into these places to study these things, to fulfill these needs. I often describe caves as the ultimate form of exploration. And it's, some people would think, well, climbing a mountain, that's a major form of exploration. Going to the moon, that's the space travel, that's the ultimate form of exploration. I would argue that cave exploration is the ultimate. The reason is that it is incredibly difficult to climb the tallest mountains. It's incredibly difficult to go to the moon and will someday reach other planets. I have great respect for the people who do that. But in those cases, the goal. You can point up to the sky and say, there's the top of the mountain, or beyond it, there's the moon. You know the goal. With a cave, the goal is the end of the cave. But where is that? What does it take to get there? You can't see it. You don't know. This photo is from a small portion of the Mammoth Cave system, the world's longest cave. Currently has 676 kilometers of known passages. And it continues to be explored. And there are regular trips that keep adding more and more. My friend here, she's surveying the cave, making detailed notes of our length, depth, sketch of the cave, what she's finding in the cave. And sometimes, here at the cave, you can easily walk through it. But further on, you see it gets a little bit smaller. In some places, you may have to crawl. In some places, you may have to dig to continue. You don't know what you're going to find. I've gone through some horribly tight squeezes and dug through areas and found nothing. The cave ended. Other times, I've dug through and found some major important new discoveries. And so that drives the human spirit, that drives your curiosity to see what's beyond, what's around the next corner. And so it's the ultimate form of exploration because you don't know what you're going to find. You don't know what it will take, to get there. The deepest cave in the world is in the country of Georgia. It's a cave called Veriovkina. It's 2,212 meters deep. This photo is not from that cave. I haven't been there. It's from a cave, a much shallower cave in Texas. But this pit going down into the cave where my friend is rappelling, is about the same size, roughly, as the entrance of this deepest cave. You can't judge a cave by its entrance. You don't know, what you're going to find until you go into it. And so in this case, she went down, she found more passages. She found the cave was biologically, hydrologically important. But the deepest cave is just 2,200 meters deep. And chances are the cave is actually much deeper. Almost certainly the cave drains to the Black Sea. And it probably formed when the Black Sea was much lower, when the water level in the Black Sea was much lower in elevation. And so the cave probably drains out, but its lower levels now are flooded with water. Now, what is the largest cave? Longest and deepest. What's the largest? That's harder to define, because when we map a cave, we survey the length, the depth as we go, and we make some average measurements of the height and width of the passages, but we really don't measure it volumetrically. I would say that for a cave, almost certainly the largest cave in the world is the Clearwater system on the island of Borneo in Malaysia. But we haven't surveyed that whole cave volumetrically, or other caves, that might compete volumetrically. But we have surveyed, and we being, the collective cave exploration, cave science community, we have explored and measured some very large rooms. A friend of mine from Britain, Andy Evis, and his crew, Rue Walters and others, have gone out looking for the largest room with LiDAR, laser surveying equipment. And so they found that the Miao room in China is the largest at 10.6 million cubic meters. Now, how big is that? Well, I haven't been there, but I have been to Sala de la Verna. It's part of the Pierre Saint-Martin system in France. And this is a photo of La Verna. And so if you look here, you see these little yellow figures. You see these, there's another yellow person. There, you see that yellow dot? Couple more yellow dots out here. These aren't actually people. These are mannequins, human forms that are dressed in bright yellow clothing, to look like people. Additionally, these ones that are far out here, these are about almost twice as tall as your average person, just so you can see them. That's how large this room is. This room is 250 meters in diameter. It's a giant sphere, and about 200 meters from floor to ceiling. The total volume is about 1/3 of the Miao room. So as large as you see this space here, it's still only 1/3 the size of the largest room. And so it's one of the things, again, that just drives the human spirit. What will you find? Will you find something large, small? Many of the most interesting caves tend not to be giant caves like this, but they may have other fascinating things about them. And so that curiosity drives us to continue to explore. We don't know how many caves there are in the world. We can make very rough estimates. I think I made a rough estimate a few years back of about 400 to 500,000 that are known, because there's no single database that collects all the information. But there are certainly many, many more still to be found. So as we continue our drive, though, our curiosity, our spirit drives us off the planet. And this is, of course, the planet Mars. And the photos that you see here are from satellite images around Mars. And from the satellites, the HiRISE as it's known, we've identified about 1,400 cave entrances on Mars. Through other imagery, we've identified about 300 cave entrances on the moon. The US Space Agency, NASA, the European Space Agency, and others, I believe the Space Agency in India, are highly interested in these caves. And the reasons are two. First of all, is the search for habitats, human and non-human. People are fascinated by the idea, does life exist on Mars? Well, the conditions on the surface of the planet are brutal. If life exists on Mars, it's going to be small. It's going to be most likely in a sheltered, moist environment, which sounds a lot like a cave to me. And it sounds that way to the space agencies. And so there's research being done in caves on Earth to understand, especially microbial life that lives in sheltered cave remote environments, to understand how it lives, how it makes its living, so to speak, and how to look for it, so that when we do put a lander on Mars or people on Mars that can explore these things, how and what to look for as we explore, the universe beyond our planet. But additionally, for habitat, there's human habitat. If we're going to build a settlement, let's say on the moon, we can't ship tons of steel and concrete and other heavy materials up there to build a shelter to protect us from radiation, from micrometeorites. We need a sheltered environment. We need a cave. And some of the caves on the moon are quite large, based on the sizes of their entrances and other factors that we've seen. And so the space agencies are looking at putting the first human habitats with lightweight material in caves on the moon, and possibly on Mars, until we can produce those heavier materials locally to build shelters and facilities on the surface. So from inner space on Earth to outer space, we are continuing our study of caves, and they still continue to be important to us. So to wrap up, this is the International Year of Caves and Karst. The International Year is organized by the International Union of Speleology, the UIS. The International Union is essentially the United Nations of cave science, cave exploration countries. We had our meeting 1 month ago in France, where we were very happy to welcome India as one of our newest member countries, represented by the Speleological Association of India, which I mentioned earlier in this presentation. The UIS created the International Year to educate the world, the public, lawmakers, land managers, teachers, students, scientists, everyone, about the importance and challenges of caves, because most people don't understand. This presentation, I offered this to Sigma Xi as part of the International Year. Now, originally, the International Year was just going to be for 2021. But because of COVID, we've extended it to the end of this year, to the end of 2022. Our theme for the International Year is explore, understand, protect. Because especially, you need this for most resources, but especially for caves. Unless you explore them, unless you know what you have, you cannot study them in order to develop the understanding needed to properly protect them and sustainably use them. So I encourage you to promote and tell people the good word about caves and karst and their value throughout the world. And if you want to learn more, you're welcome to contact the following for more information. Certainly my institute, the U.S. National Cave and Karst Research Institute. We also have a project called the Karst Information Portal, karstportal.org. This is an online library. It's a free online library of anything related to caves and karst. There are theses, dissertations, journals, newsletters, maps, government documents, all sorts of information available there for public use. And we do this project with 3 other partners, one of which is the International Union of Speleology, and here's their website. And then, of course, the International Year website, where you can go to all these for more information. So that's the end of my presentation. I'll leave this slide up here for another minute or so if anybody wants to copy these names or get a screen capture of them to check out these resources for more information. But if there's interesting questions, I've lost track of time. Hopefully I haven't lost too many of you if I've gone long. But I'm happy to answer any questions if you have any, either directly just by speaking up or if you've put them into the chat.
Oh, yeah. Hello, sir.
Okay.
Yeah. So thank you very much for such a nice presentation, and it was really very much informative to prehistoric connections and lots of stories. So really, we are thank you for this presentation. So I have some questions like You've already shown some patterns made in the Karst like that from China or in USA. So I want to ask that, can you study the patterns and can tell that what causes, like we have the rainfall data, like environment of that area, and then the patterns formed in the karst. So can you tell about that, what are the minerals can be found there or what causing these structures?
Yes, very much so. I like to quote Albert Einstein, who famously said that God didn't play with dice. He didn't take chances. He just didn't throw dice and see what happens. Everything has a reason. And it's up to us to understand what that reason is. Those patterns are not there by accident. So as we study, for those who are not geologists, there's a field known as geomorphology, the study of land shapes and land patterns, to understand why these things form, how they formed. There have been studies that have looked at the rate of erosion, that occurs under different circumstances with different forms of rock, looking at the climatic factors, looking at the vegetation. So the short answer, without getting into many details, is yes. And just because some work has already been done, people sometimes get discouraged and say, well, someone already did that. Well, yeah, they did it in their area, but it might be different in your area. You might find something new. I mentioned microbes. We're studying microbes and their effect on cave development underground, but I'm not aware of many people studying microbes and how they're affecting karst development on the surface. Maybe someone has, maybe not, but there's so much more to learn. But yeah, you bet that's something that we can do. I'm going to go ahead and stop sharing the screen. So I'll go ahead and so hopefully, if those of you who wanted these addresses have them by now, and this way I can see people when they talk. It's much nicer to see faces. And also, let me go into the chat real quick. Okay. Okay.
Yeah.
And I've just put my my email address into the chat. So if anybody has any questions, wants to reach me about anything, you're more than welcome to. So you have my address there, and so I represent certainly my institute. And up until a month ago, I was representing the UIS, the International Union. I decided not to run for another term as president, and they've got some excellent people as an excellent new person as president. But still, I still have some information about the UIS if you have questions about it. So thank you very much for your compliment there. Any other questions?
Sir, another question.
Please.
Hello. Yes.
Good evening.
So
My name
what?
is Ram Mohan. Sorry.
Okay. So please go ahead.
Sorry. Please continue.
Yeah. So another question. In the last, you shown some cast photo from Moon or Mars like that, and I presume that there still we didn't got the idea of any water erosion or some kind of thing. So what can cause this, the origin of these cast in the outer space? And can we tell something about by just studying the pictures, that what type of means geographical demography could be there, like what minerals or water or something else?
Yes, it's a good point, because what I showed you, what we know right now of the moon and Mars is not karst. It's a type of karst that we'll call pseudokarst, volcanic karst in this case. And so they occur in volcanic areas. On the moon, it's primarily basalts. which form lava tubes. We've got basalts covering much of southeastern India, and if they're fluid enough, they will form lava tubes. The way lava tubes form, briefly, is that when the lava flows, the surface of the lava will cool because it's exposed to the air. And then other parts of it will cool, but then there'll be some parts that will be the last places to cool. And the lava flows and flows and flows as the area around it becomes hard and becomes solid rock. And eventually it drains out and leaves that tube behind. And so we see these on the moon. We've known of them for a long time. There are these features called rills, which are collapsed lava tubes. And so, they're these sinuous, twisty, river-like features, but they're not rivers, they're collapsed lava tubes. So we know that they exist. On Mars, what we see are a different type of a feature known as a pit crater, a collapse that's occurred. With lava tubes, we have a better chance for going in long distances, creating a shelter. With a pit crater, it's, we may be seeing most of what's there just in the air photo because it's, it just collapsed down. And at least on Earth, we don't see very much horizontal extent of these pit craters. So right now they are not karstic. But we do believe that there is a very good chance of finding water preserved in these features. And so it's, because on the surface, because of the conditions on the surface, the chances of finding preserved water are just very small. But underground in these caves, we don't just have habitat and shelter and potential life, but we have water source. Now, we don't know of soluble rocks like limestone or gypsum at this point on other planets. But on Titan, the largest moon in the solar system, it has its own atmosphere, circles around Saturn. On Titan, the Cassini and Huygens probes of Titan have studied that. And what they found is that we have these lakes of liquid methane on Titan. And what seems to be bedrock is actually water ice. And there are features that the radar and other images show us that look very much like karst, except they wouldn't be karst in the sense of dissolving the rock, but by different processes. But it looks like we have sinkhole lakes, so it looks like we have some collapse features, but we're dealing with methane and water ice, very different situation. But so in terms of physical transport mechanisms of water, it might be, we might have some very interesting karst-like features. So I see a question from Neela. What kind of steps can be taken to prevent pollution? The best way, always, is to avoid karst areas. Now that's not always possible, and so in that case, what I would do would be I would look at your karst area. If it is small enough, then make sure that your most hazardous industries, your most hazardous activities are off the karst. For example, if you a gas station, for your car, if the karst area is small, put the gas station somewhere else. Because if the gasoline tank, at the gas station fails and it goes into the groundwater, it will move quickly and do a lot of harm. But if you are in a non-karst area, then, especially, let's say, a porous media aquifer, then the contaminants will move much more slowly, and you have a much better chance of recovering and collecting and treating that area before they do any harm. So, obviously, we don't want harm to happen anywhere, but it's in non-karst areas where you have a better chance of containing the contaminants. So your most hazardous materials, keep them off of the karst. Additionally, there is just released by the UIS, working with the IUCN, the International Union for the Conservation of Nature, we've developed these guidelines. And the name of the publication is Guidelines for Cave and Karst Protection. Guidelines for Cave and Karst Protection. They're on the UIS website, they're actually moving the location because it's hard to find right now. If you go into the UIS website, you see documents. No, you find about us and then documents, and you find it. We're trying to find it much in a place that's much easier to find. But you can search for it. They're available for free download. If you can't find them, I put my email in the chat. Just contact me, and I'll be glad to email you those. And those will give you guidelines for protecting karst in your area and in many other types of areas. So I see that there's some other questions in the chat. The next one, from Danusha. Hello there. We've been communicating by email. It says you read recently about ice caves in the Himalayas from which India's important rivers originate. How will global climate change affect the course of these rivers and, more importantly, the ice caves? Climate change is warming things up, of course, around the world. There you are. And what we're seeing is that ice in caves is melting. Certainly caves at higher elevations, like in the Himalayas, these amazing mountains, the ice there will be preserved longer than in other places. I will say that Mount Everest, the top of the highest mountain in the world, is limestone. So there's unfortunately, it's not good for karst potential because the water is frozen up at that elevation. But anyway, for caves that have ice in the mountains, those will eventually melt. So I encourage climate scientists to get into these caves and to try to collect samples, collect cores of ice as quickly as possible, if only to preserve them. Even if they don't have the funds, the resources to do the analysis or the expertise, get the expertise at least to collect them properly and preserve them for later studies so we don't lose that benefit. As far as the rivers are concerned, that's really a non-karst issue. But what we're seeing worldwide is that the glaciers are melting. The steady flow that the annual melting of the glaciers provide to support these rivers is decreasing. And so the flow of these major rivers that come through through India and surrounding region, what you've got the Ganges, the Brahmaputra, you've got the Indus, three major rivers, and then others that go further off, the Mekong and others, the Irrawaddy, but their average annual flow will decrease, and that will cause problems. At the same time, we know that weather conditions around the world will result in more extreme rainfall, and so flooding will unfortunately become more common. I'm not a climate change expert, but in general, that's what I can tell you. Comment. Thank you.
Thank you, Dr. George.
Good to meet you. And let's see. And Manya has a hand raised, so please talk to us.
Hello.
Hello. There you are.
First of all, the lecture was very informative. I really got very interested in this subject. I wanted to ask, is there any chances of technological advancement helping in reducing the pollution levels?
To reduce pollution levels, the main is, as far as technology, there are different methods. The challenge is that if you build on karst, okay, and you're doing some activity that might contaminate the water, there are technologies that prevent the contamination, but they also prevent the water from going into the ground. So if you have people who need that water for drinking, who need that water for agriculture, for industry, then they will have less water. So the trick is to find ways to eliminate or capture those contaminants, or to filter them without eliminating, without stopping groundwater recharge, keeping water from going into the ground. So there are new technologies being developed, but most of the technologies right now tend to be preventative. There are, for example, some techniques that have some limited use. For example, in my country, if you have homes being built in an area, and the runoff coming off of the streets will go into a sedimentation filtration basin. And so the water, before it goes into the stream, will filter through the sediments. The problem is that different styles of filtration basins filter certain types of chemicals and contaminants, but not others. But the other part is that any filter needs to be changed. And so people will build these things and forget about them. And then after a while, I've seen cases where clean water comes into the filter and it pushes dirty water out of the filter. So maintenance is important to make sure that the filters are clean and kept working. One last comment along these lines is that if you're not familiar with it, there's an organization called ASTM. There are two international organizations that create standards for just about everything. ASTM is one of them. And it creates standards for the chair that you're sitting on to make sure that it won't collapse underneath you. It creates standards for testing the materials on your computer. It creates standards for electrical circuits. It creates standards for just about everything. Well, I've organized a committee that's creating standards for better engineering and environmental assessment practices in Karst, so we can use these things and better we can use these standards worldwide, because most people are not trained in Karst. Most people are not trained in Karst. And so I've seen good people with good hearts, good intentions, smart people go out and really make horrible mistakes in Karst because they don't have the experience. And so we want to create some standards, so even for those who are not skilled experts in Karst will have these basic rules and guidelines to help them do a better job in managing their Karst areas. Okay, now I'm going into the chat here. To see if there's another message there. I've read that cave environments are some of those stable in terms of air temperature, humidity, and have allowed the evolution of cold-blooded organisms. I would like to know how global warming can affect this internal environments and how it might affect the long-term survival of temperature-sensitive species. Great question, because actually, in my country, the U.S. Fish and Wildlife Service is the organization that is that manages threatened and endangered species. And I have a meeting with them this week to talk about a proposal to study this exact problem. In general, what we know is that as surface temperatures get warmer, well, wait, let me backtrack one moment. The temperature of a cave will reflect the average temperature of the area. So as you go into tropical areas, the average temperatures get warmer, the caves will be warmer. If you go toward the poles or up in elevations, the average temperature is colder, the caves will be colder. So as global climate becomes warmer, then the average temperature of the surface becomes warmer, and that will translate down into the ground. What we don't know at this point is how slowly or how quickly that will happen. The other part is that we will have, in some areas, not all, but we'll have different changes in water, in rainfall throughout the region. And so that increase in rainfall will go underground. That decrease in rainfall will result in drying of the habitat. In Texas, where I've done a lot of work, especially with endangered species that live in caves, the endangered species live relatively close to the surface, within about 20 meters of the surface usually, sometimes 30 meters. But if it becomes too hot at the top or too dry because of lack of water and heat, then they will go down deeper. And you say, okay, so they go deeper. What's the problem? There may not be a problem, except that do the nutrients they get also go down deeper? We don't know. So this is a brand new field of study that I know I'm pursuing. I don't know of anyone else who studied that at this point. So I see Shweta Pal has her hand raised. So please, you're next.
Thank you, sir, for a nice presentation and information for this. And I have a question that I want to ask that although these crusts are very important for many purposes like medicinal and sources of energies, but there is also chances of the contamination of underground water because because the rock around them are easily dissolved. So how can we protect the contamination of the water, because the underground water is very important for the irrigation and all drinking purposes.
Yes, yes. And so this is something I've talked a little bit about. There's the guidelines for cave and karst protection that are on the UIS website. And again, you're welcome to email me for copies of those. Reduce or eliminate the most toxic materials. So for example, gasoline stations, any hazardous material storage facilities, any industries that use toxic materials, heavy metals, metal plating industries, for example, eliminate those from your karst areas. It's also certainly important to put in better standards, better regulations to make sure that all industries use the safest and best methods possible to prevent contamination. And so sometimes that's a matter of going to your governments and putting pressure on them to do these things. Because one of the things I've found over the years is that there are standards that can be written that says this is the best thing to do to protect your water, whether it's karst or not. This is the best thing to do to protect your water. But unless the government makes it a law and says you're required to do this, businesses oftentimes won't. They'll say, I'm not required. The law requires me something else. It will save me money if I do this other thing. To do the thing you want for more protection will cost me more money, and so they don't do it. So on the one hand, we need better technology, we need better understanding, better methods. But on the other hand, we need laws, regulations to require these better advanced methods be used. So both things go together. Oops, I don't hear you. I'm not hearing anything.
Hello, sir.
Yes, there you are.
In the karst areas, the building construction is a very risky challenge.
It depends on where you're at. In some areas where you have thin or little soil, it's not that risky. Most sinkholes that you see form, most collapses that you form, do not occur directly into caves. They are collapses of soil. And so in my country, for example, we have many sinkholes that form in the state of Florida. In Florida, you have anywhere from 30 to 80 meters of soil and sand above the limestone. And so what happens in Florida and many other karst areas is that when it rains, water moves through the soil, downward, and then it can only be a very small hole. It finds a hole in the bedrock, and it starts washing the soil down into the bedrock. Once that soil and sand gets into the aquifer, the underground stream washes it away and makes room for more sand and soil. And so as a result, you have a cave that forms in the soil and in the sand. And the soil and sand is not stable. And so what collapses is the soil and sand, not the cave. But if it wasn't for the cave below, the cave and the soil would not exist. So most of your collapses happen in areas of thick soil. And in fact, the study that I did with some friends in Florida, we found that you are 11 times more likely to have a sinkhole form around human infrastructure because of the way we manage our water. And so we don't manage the water well at times. And so we force water into one location again and again and again. And so water keeps sinking down into one location, creating a soil cave. And so the building collapses. So it's a different situation. Now, if you don't have thick soils, only thin soils and bedrock is usually very stable. It's always good to do a geophysical survey, but that's not often affordable or practical. Let's say if you're going to build, an area for homes, and it's 1 square kilometer in size. To do detailed geophysical surveys of that will be incredibly expensive. If it's a small area, one building, something like that, yeah, you can do geophysical surveys to say yes, there's a cave, avoid this spot. But in other places, it's more difficult. But in general, areas of thick soil are more likely to have sinkhole collapse than areas of thin soil. Now, I see a question here in the chat. You said sinkholes can be found in moderate to high rainfall areas, but how to distinguish such karsts, how they look in the fields, how to find them. Okay, sinkholes can be found anywhere. What I'm saying is that different types of sinkholes can be found in different areas. Even in arid areas where there is not much rainfall, you can find sinkholes. They may be rather small. They may be less than a meter in diameter and a few centimeters deep. But a sinkhole is simply a closed depression, meaning that water moves into the depression and there's not a channel for it to flow out, so it can only go down. Now, one thing to look at is there is, I don't have the website right off. Don't remember the website right away, but let me put this note here. Okay. Oops. Okay, there we go. There's, I just put a name for the World Karst Aquifer Map. It's something you can search on. It goes by the acronym WOCAM. This is a map that we developed in 2017 that I showed at the beginning of my talk. That identifies the major karst areas of the world. But what I recommend for you is you can use that and go look at that. But perhaps more importantly is to look at the geological maps of India or wherever you may live, because there may be some people not in India listening to this or who might listen to it when it's recorded. Look at the geologic map of your country, of your area. And if it has karstifiable rocks, if it has limestone, dolomite, marble, and in dry climates, if it has gypsum, if it has halite, rock salt, those areas are all prone to karst. And so those are the areas you want to have special care and attention to. But then also don't forget about pseudokarst. And again, I've mentioned it before. In India, you have the Deccan Plateau, these major basalt flows. I haven't been there. Like I said at the beginning, I'd love to go to India. Haven't had the chance yet. But not all basalts form lava tubes, but many do. So across the Deccan Plateau, which areas form lava tubes, which areas don't, I don't know. Maybe there's maps, there's information that tells you that. But at a minimum, for karst alone, limestone, look at the geologic maps. If you see limestone, dolomite, marble, gypsum, halite, you're in karst, then take appropriate precautions. So I see Ram has a hand raise.
Hello. Hello. Thank you for the great talk, sir. My question is again a follow up on my previous question about the cave environments, the temperature and humidity in the cave environments. I wanted to know, like, do caves of different length, as in the depth, have get affected differently from the changing? I mean, from the changing temperature, global warming in general. Because I was wondering if the shorter or the smaller caves will become non-functional over time, ecologically non-functional, when their temperatures rise and may not be suitable for the fauna within the cave to survive.
In general, smaller caves will be more vulnerable to change than larger caves, but larger caves can also be vulnerable if they have multiple entrances, and depending on the geometry and the elevations of those entrances, because we have something we call the chimney effect. If you have one entrance at high elevation and one at low elevation, then air will move through there rapidly. That can change. And so if the outside temperature is changed, then warmer air will move through there. It might dry out the cave more often, more easily. But in general, larger caves will be better protected from climate change than smaller ones. It also depends on a number of factors. For example, if a cave goes under a mountain, then it will be less affected by surface changes because it has much more land above it. But if the cave goes straight down and under a flat area, then it will be more affected by surface changes. So there are factors like that. Also, while we talk about caves having relatively uniform temperature and humidity conditions, in the very, very deep caves that go down hundreds of meters, you can tell the difference that it gets warmer as you go down, because the closer the deeper you go into the ground, there's a geothermal gradient, and the warmer it gets underground. Usually not a significant amount, 2-3 degrees Celsius, but that does occur. But this is something that needs to be studied, and at this point, I'm the only one that I know who's trying to study this. And so maybe you can organize a similar study in India, and we can compare results, because if I get the funding I need, it will tell us what's happening in one karst area, but that may not be enough to to say what's happening accurately around the world. It will help, but again, there's many differences in karst areas. So it's one data point, and we'll need to collect more. So
thank you, sir. Thank you. Thanks a lot.
And let's see, Nupur has a hand raised. There you are. Oh, I'm not hearing anything. Still not hearing anything. I think your microphone may be off. A friend of mine calls his computer his confuser. Okay, plugging things in. Okay, try again. No, not yet. No, I'm sorry, still can't hear anything. Okay, we've got tech support assisting. And don't be embarrassed, the same thing's happened to me too many times. You know, there's some hidden setting that I didn't know about, and yeah. Okay. All right, now you're muted. Okay. While she's trying to figure out that problem, or if you want to just, you know, put it into the chat if that's not working for you, if your microphone's not working. Are there any other questions? Either I don't see any more in the chat, or if anybody wants to just open their microphone and speak. Okay. I want to wait a moment in case Nupur wants to put something in the chat. Sheesh, yes.
Can I say something? Thanks a lot
Yes.
for such a wonderful session. And as you just sometimes back, you spoke about the collaborative projects, what you're thinking to do in US, and maybe we can do similar studies in India. But then, yeah, definitely the Speleological Association of India and other related people and organizations are interested to do these things, collaborative work. But then we majorly sometimes have a problem of funding in this country for such work, because it's not much known to our policy makers or to our decision makers. So in that case, does like your organization or some other sources of funding agencies you may suggest us?
Okay. The funding is always the biggest problem. And part of the problem is that that worldwide, caves and karst are not understood, they're not appreciated, they're not recognized as important. And that's changing. And so it changed in my country where they created my institute, but they still didn't give us very much money. So it's great to have a national institute, but I'm trying to gain more money. And so the challenge that we find in raising money is that we have to first educate people and teach people that this is important, and then convince them that it's important to them directly. And then eventually they might, you know, donate some money or provide some money for research. Many times we have to connect the money to other things. For example, as a hydrogeologist, there may not be much money to do karst hydrogeology, but there's funding to do hydrogeology. You know, to do geologic hydrogeologic research. There may not be money to protect groundwater quality from contamination in karst, but there's money to protect groundwater quality in general. So sometimes we have to go those routes. Okay. Now, my institute, we do have a seed grant that we offer each year. Depending on how much money we have, we can fund 2 to 3, sometimes 4 of them, you know, usually 2 or 3. And they're usually about $25,000, and they're to fund some specific new study in caves and karst. And they're highly competitive. So you know, we announced that on the, you know, and I've added you, of course, as we've discussed, to the NICRI email list for news and announcements. And so that's announced there. As whenever I hear of other funding sources for cave and karst studies, I publish those. But what I strongly recommend, though, is to educate people in your region, in your country, and look for money that can be applied for this, even though it may not be directly used for it. but it's that's the very hardest thing. For example, I went to the U.S. National Science Foundation to talk to them about this problem with ice caves and the ice is melting, and I said, let's go and just collect as much ice as we can to preserve it. It's going to be gone in a few years in some caves. Let's go and preserve it. And they said no, because they said we fund hypothesis-driven work. We want to understand what you expect to find in all this. And and my answer was, we're not going to find anything in a few years because it's all going to be gone. I've got some friends who are archaeologists, and they use the term salvage archaeology, where an archaeological site might be destroyed by a road or some other project. And so they go in quickly and gather whatever they can, to save as much of that culture and information. It's what I'm trying to do with ice caves. But they wouldn't fund it. They're the largest science funding organization in my country, but they won't fund it. So we're trying to find other ways to make this happen, but it's difficult. So
Yeah. Thanks.
I wish I had a more positive answer.
Thanks a lot. Thanks a lot.
Yeah. So anything else from anyone? Well, okay. It's been 2 hours since I started. And I've been glad to do this. Thank you for the many good comments and compliments. I don't need compliments, but I'm glad to see that it's useful and helpful to you. So again, you have my information, and so feel free to talk with me, and certainly talk with my friend Shirish here, who's with the Speleological Association of India. I know he'll be interested in hearing from you, and you will probably learn a lot from each other, I expect, as time goes on. So, and I think he's putting his address maybe into the chat.
Yeah.
Okay, so thank you very much, sir, for such a nice interaction, and we get to know lots of things about Karst. So if there is no other question, so let's thank all to Professor George, sir.
Okay, and there's Shirish's address. He studies birds, so ediblenest at gmail.com. So, yeah.
Hello.
Yes.
I have a question about the global climatic evolution of the Earth. That means how can I observe that from observing the topography of the caves? How can we observe that how the global climate evolves from the millions of years? Means if we observe the length and breadth of these caves, how can I conclude that how the global climate evolves from millions years?
The what I strongly recommend is, if you're interested in getting data from caves, is to talk to someone who works and specializes in this field. This way, you can collect samples that will be useful. I've seen people collect samples that simply are useless, either because they collected the wrong samples or they collected them improperly. And so, but there are people who are specialized in this, who based in Europe. There's one person who from China, but he spends part of his time in China, part in the U.S. There's a few people in the U.S. So again, feel free to contact me, and with some specifics about your interest. With most cave studies, the dating goes back about 650,000 years. That's the limit on uranium thorium methods. But there are other methods also that can be used to go back hundreds of thousands, if not millions of years. So again, it's a matter of working with someone who specializes in these in this research.
Thank you, sir.
So, and there's also the address for the Speleological Association of India in the chat. So,
Yeah.
anything else?
No, sir. I will share the email addresses to all through email. So,
Okay.
okay.
All right. Well, good luck to all of you. I wish you the best of success in becoming a new and productive chapter of Sigma Xi. I've been a member for a long time. And for those who are not familiar with Sigma Xi, it's a scientific honor society. So it looks for top-notch scientists to be involved and to contribute to the growth of the sciences. So.
Okay. Thanks, George. Thanks a lot.
Okay. Yeah. And as your shirt says, find a way.
Yeah.
It's what we all try to do.
Yeah. It says find a way or fade away.
Oh, I didn't see the bottom part. So, okay.
Thanks a lot. Have a good day.
Everyone,
Okay.
take care. Bye-bye.
Bye.